Everybody to our third tutorial of the day. It is titled Inverse Design of a Power Splitter for Silicon Photonics. Just as a quick reminder, if you guys have questions throughout this tutorial, feel free to enter them in the chat. We can also keep it dynamic. Oh, sorry, in the Q&A, not the chat. It's slightly more dynamic. And then also, if you guys in the audience have questions, feel free to raise your hand. That way we can kind of keep this slightly energetic. But with that, I will be speaking for the next hour and 15 minutes about how we can use Meep's topology optimization features to design actual devices that could one day be put and fabricated on a foundry. My name is Alec Hammond. I am a PhD candidate at Georgia Tech, soon to be PhD, hopefully in the next week, and very excited to talk to you guys. Okay, so let's talk about what we want to accomplish for the next hour and so minutes. So the primary goal, as the name suggests, is to design a silicon photonics power splitter. Now, in order to do that, we want to talk about some of the nuances with adjoint optimization, and we'll kind of put this in the context of some of the other packages that are out there, just so that we can really highlight some of the cool features that Meep has. And then we can't do adjoint optimization if we don't really understand what gradient-based optimization is or how to compute gradients. So we need to talk about that. And then, of course, we want to talk about density-based topology optimization. There are lots of ways you could use quote-unquote topology optimizations, lots of parameterization approaches. But for the purposes of this talk, we'll focus specifically on what are called density-based methods, okay? In my talk tomorrow, I'll actually talk about some other parameterizations that Meep also supports, and I'll talk about all of the different features and how that all fits together. But we'll try and limit the scope a little bit today. And then I think the most important thing that hopefully we can gather from this talk is how flexible Meep's topology optimization package is and how easy it is to prototype different kinds of objective functions. Oftentimes, it's more important to formulate a proper objective function than to use a particular tool when designing these different devices. And so we'll spend a good time focusing on that as well. And of course, we'll briefly talk about fabrication constraints and how that applies to silicon photonics, okay? So as a brief overview of topology optimization, it's a very straightforward three-step process. Step number one is where we take our original design degrees of freedom. In this case, we parameterize our design at each pixel, and we take that quote-unquote image, and we send it through a series of linear and nonlinear filters. Okay, you can think of it as various image processing steps. And you can kind of see that illustrated there on the left. I have a linear conic filter, and then I project it using a nonlinear projection function. That forms the final geometry of my device, and that's what differentiates density-based topology optimization from other topology optimization parameterizations. But once you have your final device geometry, of course, you have to port that into Meep, and you have to simulate how well it's performing according to some arbitrary figure of merit that you, the user, cares about. So in this case, we're going to be designing a silicon photonics splitter. So perhaps my figure of merit is how well I get that 50-50 split ratio, right? And you can kind of see I'm just propagating my broadband pulse through the that arbitrary geometry there so that I can evaluate that FOM. What's really cool about the way that we do topology optimization is we leverage something called an adjoint simulation. We use an adjoint variable method such that we can quote unquote back propagate through Maxwell's equations. By just running one additional simulation, we can take the results of both of those, put those together and compute the gradient with respect to as many degrees of freedom that we want. So in this case, I mentioned that this image of all these different pixels is a free parameter that we can twiddle between silicon and silicon dioxide. We can compute the gradient with respect to each of those pixels using just two simulations. And that's the key, as many of you know, to adjoint-based optimization. It's a very efficient methodology to compute gradients with respect to arbitrary figures of merit. Okay, so as I mentioned, there are a lot of different adjoint frameworks currently in the literature, out on GitHub. And so it's kind of important to understand how Meep's topology optimization interface compares with what's already out there. So for a long, long time, Stephen Johnson's group and many other groups were doing topology optimization in the context of eigenproblems, primarily for photonic crystal unit cell optimization. So there's been a lot of interesting work there. In the last 10 years, we saw some exciting work, primarily at Stanford and Berkeley, for example, using frequency domain-based solvers, both in the linear regime and the nonlinear regime, coming up with some very fascinating devices that not only were just simulated, but actually fabricated within an academic clean room environment. Very exciting stuff. What we want to focus on here is what we call a hybrid time domain, frequency domain approach, where we use a time domain solver, in this case, obviously Meep, to propagate all of our fields, but we compute the relevant adjoint quantities in the frequency domain. And we can do that very efficiently with Meep using a discrete time Fourier transform. And this is very relevant in the context of silicon photonics because most of the parameters that we care about, like scattering parameters, are already defined in the frequency domain. So it makes much more sense to use a frequency domain-based adjoint, and we can just leverage the broadband nature of the time domain solver to compute gradients at multiple frequency points simultaneously. And that also means we can compute the figure of merit at multiple frequency points simultaneously. And so that's where we kind of place Meep's context in this greater context is we use a hybrid domain approach, and we try to leverage as much efficiency as we can. Now, I don't want to spend too much of today's tutorial talking about efficiency. Primarily, that's kind of the purpose of my talk tomorrow. But today, let's try and get our hands dirty. So feel free to follow along. You can code things up in a Jupyter notebook, because that's what I'll be doing. And that way you can design your first inverse design structure. Okay, so before we go into this, let's go ahead and pull up our Jupyter notebook. So like Ardavan mentioned, all of these tutorial slides and all of these Jupyter notebooks that we're putting together now will be posted publicly after the conference. So that way, if you don't record everything now, you'll have access to it after the fact. But when we design an integrated photonic splitter, the setup is very straightforward. Okay, so in this case, I have various imports that I have to worry about. I have to work with Meep, but I also have to work with the submodule within Meep, which is known as the adjoint package, which I'm importing as meep.adjoint as MPA. And this is kind of the canonical way that we access all of the different adjoint functionality that we've been working on for the last 3 years. Okay, and if I run that, you can see that the version of Meep that I'm running is 1.25, which is the latest that we just pushed to GitHub. This is important because the adjoint solver is constantly changing state. So I'm just kind of putting it out there that this is the version that we're using for this tutorial. Okay. So now if we want to design a arbitrary splitter, there's a certain number of hyperparameters that we, the designer, have to come up with first. So for example, if I look at this cell right here, I have 2 materials that I want to design with. I have my silicon substrate that the foundry provides me with. And then I also have the silicon dioxide cladding material that goes around that, right? So I'm going to define Meep materials that describe the refractive indices. In this case, I'll just say 3.4 for silicon and 1.4 for the oxide. And then, of course, we have to describe each individual aspect of the splitter itself. So for example, let's specify the waveguide width to be about 0.5 micron because we're going to be working in the telecom regime. Let's specify the size of our design region, all of those different image processing pixels, as 2.5 microns by 2.5 microns. And then, of course, we'll specify the distance between our output arms as a micron. And then finally, this last one's important. We'll talk about this a lot later. Let's just start with a simple resolution of 20 pixels per micron, okay? So I'll go ahead and run that. And I'm trying to go at a speed that hopefully you guys can type in too, if you want to run this on your own. Okay, so the next thing that we have to think about as designers when we want to use Meep's package is if I'm working with the foundry has a specified minimum length scale that I often have to work with. So I'm pretending that we're working with Lincoln Labs just up the road here. They have a pretty cool fab, and their minimum feature size is about 90 nanometers. So I specified my minimum length to be 0.09, which corresponds to 90 nanometers. Okay. There's a few other parameters, which I'll talk about in a second, but let's just define them for right now. I have, for example, this parameter eta E, eta I, and eta D, and I define them like so. We're going to talk about these in a little bit. And then, of course, I've also specified my filter radius. This filter radius, which we'll talk about in a second, is coming from a predefined function, a convenience function that we created in Meep. We'll talk about that in a second too. And then importantly, I have this extra parameter here, which is the design region resolution. Now, what's really cool about Meep is the way that we parameterize our designs. We can do it independently of the underlying Yee grid resolution that's used to actually propagate the fields. So in this case, I want a really fine resolution for my design. That way I can, at the end of the day, export it to a nice GDS file and ship it off to the foundry. So because of that, rather than using a simple 20 pixels per micron, let's upsample it by a factor of 4, okay? So that we can get 80 pixels per micron. That's where my design region resolution comes in. And then I can specify the number of pixels in the X direction, number of pixels in the Y direction. And then finally, we start getting into new code that you may not have experienced for you regular Meep users. And that is, how do we specify where this design region is going to be, okay? So we have to specify our design variables, these individual pixels that we're going to be twiddling on and off. And we use a special data function in Meep that we created over the last couple of years called a material grid. And the cool thing about this material grid is we specify the dimensionality of it arbitrarily. So in this case, I'm saying it's a 2D image, an nx by ny number of pixels. But if I wanted to, let's say I only wanted it to vary in one dimension, I could have just specified nx for example. And then Meep will automatically project that design grid into however many dimensions you're actually simulating. So in this case, I have 2D degrees of freedom. And if I were to do a 3D structure, it would automatically project that into the third dimension, which is what you typically get when you're designing a silicon photonic splitter, right? That lithographic plane is defined by the foundry, not by us. Okay, and then of course, we also have to specify the two materials we want to interpolate between. In this case, our cladding material, silicon dioxide, and our silicon. And then finally, our design region, we specify here as well. I won't go into too many details there. Now, this might seem a little monotonous, but I want to try and highlight the simplicity of the fact that it's very straightforward to jump from normal Meep users to topology optimization just by altering a few lines of code that we're very familiar with. So in this case, I'm just going to take a lot of the same code that Artavan showed in his tutorial, where he set up his grading structure, where I just define the size of my simulation cell, the size of my PML layers, for example. Earlier, we specified that we wanted to simulate over 100 nanometers of optical bandwidth. We started at 1500 nanometers, and we're ending at 1600 nanometers. So in this sense, in this case, it makes sense to use a source that's defined right there in the middle, about 1.55 microns. And make sure that it's broad enough to cover all of those frequencies that we want to cover in our objective function. So all of this is very straightforward. We implement our geometry objects as well, and we finally formulate our simulation object, okay? So I'm going to go ahead and run this cell. And my MacBook just turned 10 years old this month, so it's actually pretty fast today. That's great. So if I look at this picture right here that I just generated, this is a representation of the geometry that we just coded up, the simulation object. And if we look closely, those green hatches are the familiar PML layers that we have. And then it looks like I have an input waveguide, two output waveguides, and then I have that red line, which is, of course, the input source that we're using to excite things. But it doesn't look like I have a design region there, right? And that's actually kind of expected, because when I initialized my design variables, they were all initialized to 0, which corresponds to the silicon dioxide. So you can't see the design region there because it's all glass. But I can arbitrarily change my design variables to look like whatever they want. So for example, if I grab some code from down here, so I want to keep this dynamic, and I'll bring it up here. And let's change this to a nice uniform mapping like this. So I have a set of an image, essentially it's a gray image that I want to plot. Let's see what happens if I decide to plot it after the fact as well. There we go. And now you see that we have our design region there. That gray represents what we call an artificial interpolation between our two materials that we're trying to design between, silicon and silicon dioxide. Okay, the refractive index is literally in a linear interpolation of those two refractive indices that we prescribed earlier. But what's cool is I can arbitrarily choose any of those pixels and twiddle it as I wish. So for example, if I do something like this, .rand. Okay, I have a bunch of random pixels now specified with different refractive indices there. And of course, this doesn't correspond to a physical device. But there are some exciting fabrication platforms that are emerging, actually from MIT, that let you arbitrarily twiddle the refractive index in a continuous fashion over 3D geometry. So at least we also have that flexibility at our disposal. Okay, but in order to actually optimize our structure, there's a few things that we have to take into account. So first of all, we soon have to define a figure of merit that tells us how well our geometry is performing. But before that, we have to figure out a good way to kind of play with these design degrees of freedom. Because as I mentioned earlier in my presentation, we have to use a series of linear and nonlinear transformations to adequately represent our geometry. And there's a lot of reasons for this. So if you look here, I have a set of degrees of freedom at the top there represented by rho. And I send those through various different uniform filters on the left, conic filters on the right. And you can see that the actual filtered field, of course, changes depending on the kernel. And then if I decide to project that design using, for example, a tanh function, then the final design degrees of freedom that the Maxwell simulator solves for is completely different, right? So the choice of the filter kernel has a lot to do with what the design at the end of the day needs to look like. So we need to come up with A, why do we need to filter in the first place? And B, what filter kernel should we choose? And there's two reasons we want to filter. Number one is actually a bit unintuitive, we want to filter our design degrees of freedom to help regularize the optimization process. If we just decided to optimize the raw degrees of freedom, we would see a lot of very interesting optimization results that quickly jump into local minima, and it's really hard for the optimizer to jump out of the local minima. But by doing things in this fashion, by first running it through a filter, we actually spread the energy out in the back propagation stage. We spread out our gradient through all the degrees of freedom such that there's a bit of locality in each of our degrees of freedom there. The second reason we want to use filters is because this is a clever way that we can implement minimum feature size constraints, which is absolutely essential when you're designing silicon photonic devices. Okay. Let me stop here. Does anybody have any questions that they want to pipe up? Okay. So if we want to adequately map our design degrees of freedom, luckily we have Python at our disposal, which means we can use the full flexibility of this differentiable environment to arbitrarily choose how we filter and project. So in this case, I have a very simple function that I defined called the mapping function, which takes as an input x, which are our degrees of freedom, but it also uses those parameters I talked about earlier, our eta and our beta. We'll talk about those in a second. But I want to talk about how easy it is just to create a function like this that takes all of our design degrees of freedom and runs it through those different filter steps I was talking about. So this first line right here does an interesting thing. I know that I want to do a 50-50 splitter, which means I can induce some sort of geometric symmetry across my design regions, and that will ensure that the splitting ratio will be equal. I might have some additional insertion loss, but at least the splitting ratio will be 50-50, right? So what this line of code does right here is it takes those design degrees of freedom, it flips them, and it averages them together. And the result means that the final geometry has to be symmetric across that axis. Okay, then the next line is very straightforward. I take a simple conic filter, which we defined in Meep for convenience, and I just take those mirror image degrees of freedom and I just run it through my filter. And then finally, I use a tangent projection function, which we also conveniently define in Meep, and I project those depending on these two parameters here, eta and beta. Eta tells me where on that tangent function I want to project, and beta tells me how steep that projection function actually is. So for example, beta of infinity corresponds to a Heaviside step function, right? And the downside with the step function, of course, is it's no longer differentiable and there's all sorts of problems, right? So the challenge with density-based topology optimization is slowly ramping up this binarization constant in such a way that the design remains differentiable, but it's still binary at the end of the day. Okay, so there's a lot of art that gets mixed into this, and we're going to talk about that once we start getting a little bit more hands-on. Okay, so now let's take a look at this this function. Let me see if I can actually implement it when I update my design region. I should probably run the function itself first, and I'll update the parameters. And I should run this one first. Let's go like this. So under the hood, Meep has the ability to leverage two different automatic differentiation tools. The default tool that we typically use is AutoGrad, but as many of you know, AutoGrad is no longer maintained or supported. So we also have support for JAX. In this particular example, I'm going to stick with AutoGrad. I'll run that right there and make sure I spell it right. There we go. And let's do something interesting. Let's do a random design, a random row to keep our nomenclature consistent. And use the proper libraries and get rid of this 0.5. And we see now that rather than the original design that we saw that was random in the whole design region, there's clearly a symmetry condition through the middle of the splitter like we'd anticipate. And something else that's important is that this particular randomness is actually smeared out according to the filter radius that we specified earlier. And that filter radius directly corresponds to the minimum length scale of our foundry. So if our foundry has a really large minimum length scale, let's say we're working with a very old foundry, then the filter radius is also going to be correspondingly large, okay? Which obviously affects the kinds of fine features that we can expect throughout the optimization process itself, not just the binarization at the end of the day. So now let's play with some of these other parameters that we have right here. Like this 2 right here corresponds to our beta, which is our binarization constant. Let's do it something really, really high, like 128, and let's see what happens. Now we can see that that same design is significantly more binary thanks to that tanh function that's running through there. And if I play with, let's keep that 128 the same, but let's change our eta parameter, which means we shift the location of that tanh function. So I'm going to go to something like 0.7. Oh, that was too much. Let's do 0.51. So in this case, we can see that everything looks slightly eroded. And let's go the other direction. Let's go 0.48. And now everything is slightly dilated. Okay, so that's the advantage of using this tanh function by shifting it using that eta parameters. We can very easily erode and dilate our design. Okay, there's actually slightly other ways that we could do the same mechanism in a more deterministic fashion, which I'll talk about tomorrow. But it's good to be aware that we have lots of knobs at our disposal, but each knob does a very important thing, and it takes time to adequately swap between these knobs. Okay, so it looks like we have a way to take an existing Meep simulation and arbitrarily parameterize at each individual pixel. We can run it through a series of linear and nonlinear filters, and we have a lot of flexibility as to what those filters look like at the end of the day. Okay, so, and we already went through different ways that we could perturb those parameters. One thing that we could do is we could look at different optimization functions that Meep has provided as well. So if we look here, inside of the Meep code itself, we have a file that we provided called filters.py that has several different filter kernels predefined. So earlier, I used a conic filter, which is defined here, where we pass in our minimum length scale, which corresponds to the radius, and then the size and the resolution of the filter. But there's other filters that we can use too. We could have used a Gaussian filter. We could have used, I'll just scroll up because that's easier. We could have used a cylindrical filter, and you, the user, could actually arbitrarily define any kind of filter that you want. There's lots of different projection functions that we have at our disposal. We have this tanh projection function, a Heaviside projection function, which looks a lot like a tanh projection. So again, we have a lot of predefined functions for you for density-based topology optimization, but there's also a lot of flexibility in case you want to prototype something new. In fact, that's where a lot of the innovation with density-based topology optimization has come in the last 15 years, is being able to arbitrarily try different filter functions or different projection functions. So if we go back here to our notebook here, if I can somehow get there, let's see. There we go. Okay, so now let's talk about our optimization problem itself. Now, the optimization problem needs to describe the quantities that we, the designer, actually care about. And as I mentioned earlier, let's start with something simple. Let's start with just the monitoring the power output of our splitter. We're going to ignore the phase. We don't care about the phase right now. And I just want to minimize the insertion loss, essentially. Because I have the symmetry condition, I can ensure that it'll be a 50-50 splitter, right? So one way to do that is we take those eigenmode overlaps that Artavan talked about in his last tutorial, and we can place eigenmode overlap monitors over the output waveguides. And that's what we do here in this piece of code. So I define 3 eigenmode overlap regions. I have my TE0, which corresponds to the input waveguide, and then my TE top and my TE bottom, which corresponds to the top and bottom waveguide. And we'll visualize this in a second. Don't worry, it's a little hairy right now. Okay, but I have all of these different eigenmode coefficients. And the reason we want to have an overlap on the input waveguide is eventually we want to actually compute a scattering parameter. And to do that, we need to take the eigenmode overlap of an output and divide that by the eigenmode overlap of the input. And this is a very easy way to do that. So now that I have these 3 parameters, these 3 eigenmode overlaps, let's programmatically define our objective function. And this is the real power behind, in my opinion, Meep's topology optimization toolset, is how easy it is to define this objective function. So in this case, my objective function I'm calling J, and it's a function of 3 arguments, the 3 eigenmode overlaps that we previously defined. And we notice that source, top, and bottom correspond to these 3 arguments in this list. They don't have the same name, and that's okay, because we can arbitrarily name what these arguments are going to be, but we just need to know that the first argument of our objective function corresponds to the first quantity of the list of objective arguments here. And in this case, I'm computing, this looks like an S12 parameter, this looks like an S13 parameter, and I'm looking at the power there, and I'm just going to maximize the power of both of them. And because I have the symmetry condition, I could just sum the 2 powers together. And then if you notice here, I have a mean, an autograd mean function, which is going to take the average power across all wavelengths, because we are doing a broadband simulation. We're specifically simulating over 5 frequency points. So we can look at the power at all 5 of those frequency points simultaneously and optimize the mean. Later on, when Mo gives his tutorial, he's going to talk about alternate ways that you can optimize multiple frequency points in tandem and some of the distinct advantages to other norms than the L2 norm in this case. But for now, let's keep things simple and easy. We'll start with the L2 norm by just taking the average. And then we'll formulate this new object, which we recently added to Meep in the last couple of years, called the optimization problem. And it's very straightforward. All we have to do is provide the simulation object, the objective function, the objective arguments, the design region, and of course, the frequencies that we care about. And we have this cool plotting feature, just like we do with our normal simulation object, where we can visualize not just the geometry and the sources, but we can also visualize the actual blue monitors corresponding to our eigenmode overlaps. So if you can kind of see there, maybe I'll try zooming in a bit. This blue monitor corresponds to our input eigenmode overlap. And there's actually 2 that are right next to each other right here, 2 eigenmode overlaps corresponding to the different waveguides on the output. And then you notice that there's also a DFT region here that encompasses the entire design region itself. And the reason that's showing up is because we actually have to store the Fourier transform fields within the design region for both the forward and the adjoint simulations in order to compute the gradient, okay? So that's why you see that in that area right there. Okay, so now let's talk about the meat of what we're doing here, which is to compute an actual gradient of this structure right here. The figure of merit is the average power going through both arms summed together. And I want to compute a gradient based on this structure right here. So all I have to do is provide an initial condition to initialize this. Let's not do this initial condition. That's a little wonky. Let's start with just a simple gray geometry like I showed you earlier. And all we have to do is pass that into our optimization object, and it'll return 2 values. It'll return the objective function FOM evaluation, and it'll also give us the actual gradient itself. So I'm going to go ahead and run that real quick. And you can see there that, so starting my forward run, which hopefully doesn't take too long. Again, my laptop's a little bit older. Oh, see, that was actually pretty quick. Now it's already doing my adjoint simulation. Okay, and you'll notice that the adjoint simulation on average will take slightly longer than the forward simulation, particularly for broadband simulations. And there's an important reason behind that. I'll talk about the nuances in specific tomorrow, but just be aware that in order to create these adjoint sources that go in the adjoint simulation, we need to make sure that they cover the same broadband spectrum that our figure of merit does. And in order to mathematically do that in a way that was deterministic each time, sometimes those sources take significantly longer to converge than the forward run does. And so we're actually looking on ways that we can optimize that in the future, and we'd love people to help collaborate with that effort. Okay, so it's still running the adjoint run, but that's okay. In a second, we'll talk about how we can it'll automatically take the results from the forward run and the adjoint run, and it'll recombine those under the hood to provide us with our gradient at each individual wavelength point. And so while it's doing that, oh, actually, it already finished. Perfect. So you can see it's calculating the gradient, and the actual step to calculate the gradient in this case was rather quick. Okay, so finally, let's do this. Let's go ahead and visualize the gradient. Okay, that right there is the gradient of my figure of merit with respect to all my degrees of freedom after just 2 simulations. And there's a couple key observations that we should take here. So that color bar on the right tells us the relative magnitude of our gradient, right? So we're looking at values of 10 to the minus 3 to minus 10, actually, yeah, really close to 10 to the minus 3, and both positive and negative. But if you look at the color there, you'll notice that there's a lot of values that are just 0. In fact, it looks like a very sparse matrix. Most of the gradient is indeed 0. And that's completely to be expected because our design grid resolution is significantly higher than the underlying Yi grid resolution, the actual FDTD solver. So most of our design degrees of freedom actually aren't directly contributing to any gradient calculation itself, right? But if you recall, we used a filter operation, and this isn't actually the gradient with respect to our actual degrees of freedom. This is the gradient with respect to our projected degrees of freedom. So if we wanted to get the actual gradient, we have to backpropagate through the entire chain. We have to backpropagate through the projection function and the conic filter that we used. And luckily, Meep makes that very easy because we leverage AutoGrad under the hood. There's this fancy function called a tensor Jacobian product, which is a nice way to do lots of vector Jacobian products. And that's all we're going to do here. I'm going to take my mapping function that I defined earlier, pass it in here with all the parameters that I used, and I'm going to automatically just backpropagate through it. And the actual gradient that I care about at the end of the day looks like this. And you'll notice it's no longer sparse, and it's much more smeared out like we would expect. Okay, so what's really cool about this is as I'm prototyping with different filter functions, I can easily compute the gradient with respect to all of that using this AutoGrad pipeline under the hood. Okay, so AutoGrad and even JAX have two important advantages. It helps me easily compose objective functions, and it also helps me easily compose the density-based functions that go during my parameterization stages right here. All right. So before I talk about optimization, I want to take a break here. I noticed that there's a question in the Q&A. Stephen, did you already answer it? Perfect. Let's go ahead and take a, this is from Ben, I'm assuming at BYU. He says, are there situations where you use a different filter from conic? I know Meep also has a cylindrical and a few other filters. Yeah, good question, Ben. So as we saw, Meep does indeed have lots of different filters. And there's different reasons you would use different filters based on what you're trying to accomplish with respect to, for example, minimum feature sizes. Okay, if you wanted to incorporate a minimum feature size constraint, that constraint is based on the underlying filter kernel. And maybe the mathematical constraint that corresponds to that filter might be better conditioned for a particular problem, for example. But Stephen, have you ever encountered a problem where a filter performed better than another filter, for example? Yeah, the reason we use conic filters is because all the math has already been worked out for us for the constraints for a conic filter. So we didn't want to rederive all of that. Yeah, and it's a separable filter too, right? So yeah, there's a lot of reasons we like conic filters. But Ben, feel free to implement a different filter if you can think of one. Perfect. Thank you. Are there any questions? Yeah, Arjun.
What's the advantage of defining your symmetry in the mapping function versus using the built-in symmetry?
Yeah, so his question was, what are the advantages of defining the symmetry in the mapping function versus a lot of the symmetry conditions that Meep already supports? There's actually two reasons. Number one is because there's a current bug in the code, which we recently reported. We've been adding a lot of features to the code base, and along the way, we've been breaking some things. So previously, you were able to take arbitrary design regions and overlap them over each other, and it'll automatically average them for you at the end of the day, like what Arjun is suggesting right now. Oh, I'll talk about that too. Yeah. And because of that, there's a bug there. And then the other flip side to that is, you know, we could have used a Meep symmetry condition itself, not just a geometric symmetry, but a simulation symmetry, because there's symmetry with the fields, right? And again, the reason we didn't do that is because there's also a slight bug with the code. We made it more performant, meaning we could do much larger structures now than we could have before, because it distributes the memory better. But we forgot to account for those symmetry conditions. So we'd appreciate your help with that on Friday.
The Meep symmetry is only supported in a really small set of things. You can't have diagonal.
Yes, yeah, so what Stephen was saying is Meep supports a small subset of kinds of symmetries, like rotational symmetry, C4 symmetries, or mirror symmetries, for example. But the Meep grid is much more flexible in the kinds of geometric symmetries that it can compose. You can arbitrarily rotate your grids at arbitrary angles, for example, and place them all over the place. You could take a particular grid and replicate it, and it'll map to itself each time. So that's an important distinction between a simulation symmetry and the symmetries within the geometric parameterization itself. Yeah. Another reason why we don't typically parameterize or you put the symmetry in the geometric block itself, but we like to do it in the mapping function. I find that if you do it before the projection function, you lower the risk of getting weird averaging after the fact. In theory, if you optimize using perfect symmetry conditions, you should never get weird averaging, but nothing in the code is perfect and you always get some weird things. So I like to keep it safe by putting my mirror conditions before my projection rather than after my projection. Yeah, great question, Arjun. Any other questions at this point? Perfect. Got lunch sitting through us. All right, so now let's talk about the real reason we're here, which is to do some actual optimization. Okay, so let me zoom out a bit. There's lots of different, in fact, let's go back to the slides here real quick. Before I talk about the optimization, I want to hit on one more important point about the flexibility of our filters. In this particular example here, I actually have two stages of filtering and projection as opposed to the single filter and the single projection that we recently used. And this is a technique that was kind of pioneered by Rasmus Christiansen at DTU to help regularize a lot of wave-based physics problems. It's really difficult to preserve a minimum feature scale for a lot of wave physics problems, and this is a way that he got around it. And what's cool about the way that Meep works is you can arbitrarily specify as many filter stages as you want inside of that mapping function. So if you're interested in that, please take a look at his paper. So finally, let's take a brief look at the different optimization methods that we have at our disposal. Obviously, Meep's adjoint method is giving us a gradient at the end of the day, so we better use a gradient-based optimization algorithm. But that alone isn't very sufficient to help us know which algorithm we should use. There's lots of different algorithms out there. For example, in the machine learning world, they use a lot of line search algorithms, things like gradient descent, or they might spice up gradient descent by putting momentum terms, for example. But if you recall, us silicon photonics designers are often working with lots of different fabrication constraints, which means we have optimization constraint functions. And a lot of those algorithms aren't directly compatible with nonlinear constraint functions. You can augment your objective function, for example, with that constraint function, but the optimizer itself doesn't natively support those. So we prefer to stay away from raw gradient, vanilla gradient descent kind of algorithms. There's other algorithms that are very sophisticated, for example, like SQP and interior point algorithms. But the algorithm that we typically use is what's called a Ccsa algorithm, which is has a lot of nuances with it with regard to how it compares to, it's most closely related to an interior point algorithm. But one of the reasons why we like it is it scales incredibly well to really large problem sizes. So in the case where we have hundreds of thousands or even hundreds of millions of degrees of freedom, to compute each optimization step is rather cheap using a Ccsa algorithm. And the other reason we like to use a Ccsa algorithm is Stephen Johnson coded up a very nice rendition of it within his open source library, NLOpt. And that's what we have here. We have NLOpt started to get set up within our code base. It has a nice Python wrapper, and it plays really nicely with Meep. So we're going to use the Ccsa algorithm, and we need to define a Python function that takes all of the Meep data and puts it in a nice packaged format for the NLOpt optimizer. Okay, and that's what we're doing in this cell right here. So we have our objective function, which I'm calling f, and it's a function of v, gradient, and our current beta. So v is just the current design parameters that the optimizer wants us to try out, and we're going to return to it the gradient. And we also need to pass to it the current beta that we're on, because as we know, we're eventually going to step through beta at different values so that we can gradually increase the binarization. Okay, but once we compute our gradient like we showed earlier, once we get our objective function and our gradient value, we need to be sure that we backpropagate through that using our tensor Jacobian product. And we also want to make sure that we can kind of visualize the evolution of our design after each optimization iteration. To compute the gradient, it took about 90 seconds last time. So it'd be nice if we can kind of just see images as it progresses to make sure that it actually is doing what we want it to do. So that's what this piece of code right here is doing. And then this is just some boilerplate stuff here to help store the evaluation of our objective function so that we can track what the performance of our device looks like as a function of optimization iteration. Okay, so I can go ahead and run that cell right there. And then finally, this is the most important part of our optimization is the actual optimization step itself. So I'm going to define the MMA algorithm, which is a subset of the Ccsa algorithm. I'm going to define some initial conditions and some lower bounds and upper bounds. I want to make sure my design parameters stay between 0 and 1 so that they play nicely with Meep's projection functions, which handle all of the interpolation, assuming that your design parameters are bounded between 0 and 1. And then I'm going to set a way that I could evolve beta in a rather predictable manner. So I start with 4, and I slowly ramp that up by a factor of 2 each time. That's what you can see through this code right here. And all I'm going to do is I'm going to set up a simple loop where at the end of each loop, it's just going to update beta. But during that loop, it's going to do a quick little optimization of just 12 iterations using the Ccsa algorithm. And at the end of those 12 iterations, it's going to take the winner of that optimization and use that as an initial condition for the next optimization, but with a slightly higher beta. Okay, so rather than actually run this optimization, I ran it last night ahead of time. And you can see, let's start going through some of the results here. So this is the initial condition that I used. I used a 0.5 gray region all throughout, and this is pretty common within topology optimization. And you can see that the first couple of iterations don't seem to be perturbing the optimization much. But once we get to optimization iteration 4, we quickly see that the geometry is starting to take some interesting form based on the diffractive nature of the 4 and the adjoint runs that are interfering, right? And very quickly, it's starting to naturally binarize as well. Okay, and then we can start to see that maybe it starts to back up a little bit because it overstepped. and it starts to refine its performance, okay? And then once we get to iteration 11 and 12, we realize that we need to up the beta, and things start to get slightly more binary because we're using a higher value of beta. Our tanh function is slightly more steep. And we can see this process continues until we get a slightly more and more binary design. And I'll skip towards the end right here. I'll fast forward. It's too bad my computer's not really this fast. And then you can see it's starting to get really binary and has some very interesting features. Now, the final structure that I converged on here, you'll notice, still has a bit of gray. These regions right here are nice and black, but it's actually trying to set the edges of our design region with these black pixels right here, the silicon regions. And there's definitely regions that are violating my minimum length scale constraints. Okay, so there's still a lot of issues that we need to talk about in a second. But we do have a fairly interesting looking device, and let's see what the final device performance looks like. We can track that the splitting ratio as a function of iteration indeed converges to about 3 dB. It's a 3 dB splitter. And then we look at the final splitting ratio as a function of wavelength over our 5 discrete wavelength points. And we see it's about 46, 47% across the band. So it's not a perfect splitter. So we should talk about, why didn't it converge all the way to 50%? And then how do we make this more fabricatable, completely binary, and things like that? So that's what I want to focus on the next 10 or 15 minutes on, is kind of discussing slightly the art of inverse design rather than just the mechanics like we've talked about so far. Before I do that, though, do we have any questions? Okay, perfect. Okay, so first of all, why didn't we get a slightly better performance? We could have, for example, rather than evolving beta at, let's say, 12 iterations, we could have done significantly more iterations per beta, for example, 60, 70, 80, or until it reached some convergence criteria, right? And for example, maybe the design stopped changing by a factor of 0.1%. So there's lots of different hyperparameters like that we, the designer, need to tune in order to effectively get a higher performing device. In this case, we only ran it for 72 total iterations, right? So it's a natural trade-off between how much time we want to put on our computation clusters, which cost money, and what our actual figure of merit is from a fab perspective, okay? But the other issue is we noticed that the design wasn't completely binary, right? And it didn't satisfy our geometric length constraints. And if we actually use the geometric functions that Meep provides as nonlinear constraint functions, it'll actually solve both those problems for us. It will ensure that the final design at the end of the day is completely binary, and it will also ensure that we have a minimum length scale, both line width and line spacing, that's perfectly satisfied. And I'll talk about more of those nuances tomorrow. Okay, so briefly, let's talk about how we could alternatively formulate our objective function. So this is the first way. We said, let's do a mean squared error approach where we just sum the powers across all our different wavelength points. And let's just try and maximize that. It's a maximization problem, not a minimization problem. There's another way that we could have done this. We could have tried to condition our optimization problem using a log function, right? Sometimes we like to look at things in dB scale, especially for power levels that need to go really far down. For example, in our lab group, we designed silicon photonic splitters that had 20 dB of separation between one arm versus the other. So that 1% tap needs to be very, very accurate. And it's really hard to do that using just a simple 1% and 99% value. In this case, if you put everything in log scale and look at the dB values, you help condition the optimization problem, and the optimizer might have a better chance of actually finding a design that satisfies that. Okay, another approach, which Mo will talk about in his talk, is what we call the Minimax approach. Rather than using the mean squared error, the L2 norm, we could use the infinity norm, where the optimizer focuses on the worst performing case. And then another option is to do a multi-objective optimization where we could look at each arm independently. This is especially important if you want to do like the 99-1 splitter I mentioned earlier. You can do 2 independent objective functions, and Meep can either optimize both of those in tandem. Like let's say you have lots of compute nodes. It can do both of those in parallel if you want, or you could just feed them in and it can do them serially, and it actually caches the forward run because it only needs to do 1 adjoint run for each additional objective function that you specify. Okay, so there are a lot of publications that we've released in the last few years that kind of describe some of these features. About half of these focus on the theory behind what I just showed you, and the other half are actual experimental demonstrations on lots of different gradient couplers, polarization splitters, rotators, on actual commercial foundry platforms. So it's very exciting that we've actually validated this technique, not just from a theoretical perspective, but also experimentally on large scale foundries. I'll talk, this will probably what I'll be focusing on in my talk tomorrow. And if you guys have any other questions, I look forward to hearing them now. Thank you. Oh yeah, go ahead, Ryan.
So in this tutorial, we said design region in vivo, and where
That's right.
I imagine there's some art and heuristic in deciding how our design region wants and when to change it. I don't know. Have any more fast.
Yeah. Yeah, so let me repeat the question. Ryan pointed out that we very early defined our design region to be 2.5 microns by 2.5 microns. And he correctly postulated that that's kind of an important parameter that will affect the optimization evolution and requires a little bit of a priori knowledge on what value to use ahead of time before we start the optimization. And that's absolutely correct. And to kind of help gauge with that, this is something that we call a hyperparameter, right? Something that isn't directly optimized by the optimizer, but is in turn optimized by the human controlling the optimizer, right? And there's lots of ways that people do hyperparameter optimization. They'll wrap their optimization within a larger optimization to kind of tune these parameters. For problems like this, that's not always the best approach. Typically, it comes down to the physical designer intuition, which helps us depict what that should be. So in this particular example, I might say, hey, the performance I'm getting at the end of the day, I only got 46%. I bet you, like you said, Ryan, it's because the design region is too small. There's not enough room or wave action for us to maximize that. So I'm going to bump it up to maybe 4 by 4 microns. But I also know that that's going to take slightly longer in my cluster, so I need to make sure I have enough credits. You know, there's that calculus that always needs to be considered. There's other hyperparameters that many people don't necessarily consider, which are even more significant than the size of the design region. For example, in the case of the splitter, you have the separation between the two output arms. That has a drastically affects the performance of the device. The closer those arms are together, the easier it will be to get that 50-50 split ratio, right? But the downside with that then is then you have to adiabatically transition those outside of your design, and you might get some cross coupling there. You might have a directional coupler at the end of the day. So you need to kind of balance out the end of the day requirements, which is I need to have a device with S parameters that are perfectly self-consistent with the optimization constraints, which say, hey, I need to get this done in the next 24 hours. Does that answer your question, Ryan?
Yeah.
Okay, perfect. Thank you. Yeah, Flores? Oh, that's a good, yeah. So you do get 50-50. Okay, let me repeat the question first. Flores points out, well, if we enforce the symmetry, how come we don't have 50-50 split ratio? We do have a 50-50 split ratio. What I was showing was actually the insertion loss in each arm, right? So I was only getting 40% power through each arm, right? So that translates to about a 4% loss in each arm, right? Yeah, that's a good question. I should have clarified that. You have a follow-up question? Yeah. Yeah, let's go to. So what we just did on our notebook was all 2D so that I could do it on my MacBook, right? But I've done literally hundreds of 3D simulations on clusters. What you see right here, these are 3D, for example. This is a 3366 splitter that helped us design a Stokes vector receiver for a commercial platform. And then this on the right is a polarization splitter. You can see there's actually 2 layers there. The bottom layer is the standard silicon on insulator layer, and the top layer is the polycrystalline layer, which is typically used for the gates of a MOSFET. And we can, in tandem, optimize both of those layers such that we can maximize performance. This is especially important for polarization devices to break that Z symmetry so that you can route different polarization states to different locations. So to answer your question, that's a long way of saying, yes, we do a lot of 3D optimization all the time. That's always been our end goal, actually. Yeah. I've in the past, I've done maybe 4 or 5 etch. So let me repeat the question. He's wondering, obviously we're showing here 2 different material layers. Can you also do different etch depth layers? And the answer is absolutely, you can. You can do as many etch depth layers as you want. You can do as many material layers as you want. You can do different materials themselves. In this case, these are both silicon, for example. One of them is just polysilicon. But you can also do lithium niobate. You can do 3.5s that are on there as well. There's a lot of flexibility. Yeah, Ryan?
I could imagine finding on accident some structure that's got a lot of reflections, maybe building up some kind of band or resonance, and you wait a long time. What this one's doing under the hood is just waiting long enough.
Yep. So the question is, we're doing a time domain simulation. So how do we know we ran the time domain simulation long enough such that the fields actually converge, right? And this is something that we've battled with for a long time. Under the hood, we have this function that takes care of this for us, where we actually track the convergence of the DFT fields. Okay, so we measure all of the regions that we're measuring DFT fields within the simulation domain, and we track how they're changing as a function of time. And once they stop changing by some threshold, which we decide, then we know, oh, okay, we've ran it for long enough. That's actually the steady state response at that point. We can use that now for our adjoint calculation. Now, there is a caveat with that, like you suggested. What if you have a really resonant structure, right? Where it takes a long time for something to queue out. That's just kind of a trade-off with using a time domain-based code in this approach, right? Is you really do have to wait for those queues to completely converge. There's lots of approaches to counteract that, which hopefully we'll be tackling in our developer session this Friday, using, for example, Pod A approximates, where you only need to record the time steps for a certain amount of time, and then you realize, oh, I can just extrapolate beyond that because it's very predictable, right? But that requires significant software engineering effort, and hopefully we can get that implemented soon. Yeah, let me just repeat what you said. Stephen also said that you're not going to get high Q structures by accident. And most of the time within integrated photonics, we don't want high Q structures. We want things to be very stable across a long bandwidth, right? Because high Q structures are very sensitive to fabrication variability. But Stephen, you said there was a question in the chat? All right, let me see here. And the Q&A, yes. Okay, there's another question from Ben. Will using multiple frequency points versus only one frequency point in an adjoint solver iteration give different figure merit results for the center frequency? Great question. Yeah, okay, just want to make sure I got that. In theory, it shouldn't, right? But there is a slight difference in implementation between the two based on the DFT convergence. Because when you're only doing a single frequency point, you are only looking at the convergence of that one wavelength point, right? So if you do multiple frequency points, you have to wait for others to converge too. And it could be that the other wavelength points force you to run the simulation slightly longer, or it could be that the adjoint sources that we created based on this fit, which I'll talk about tomorrow, don't have the same kind of accuracy as a single frequency. So you will see some slight differences between the gradients there. Obviously, the structures will be completely different, but the gradients should be pretty close to each other. So for example, we only care about our figure merit of 1550. With the figure merit function evaluates different values of 1550 if we use one frequency point versus if we use many frequency points in the adjoint solver. I'm mostly thinking about differences due to binning of the fields over the frequency spectrum. Do you have any insight, Stephen?
I think this is not. It's not due to binning. That's not how this works. It's not like if you add more frequency points, then somehow it's changing the definition of the Fourier transform at those points, like it's doing some filtering. There's no we're not collecting like we're not like filtering it and then integrating all the thing in some frequency bin, right?
In other words, it's not a DFT, it's a DTFT, right?
I mean, well, I'm not sure I would put it that way, but the point is that yes, if you whatever frequencies you specify, it's computing the DTFT at those frequencies and at those frequencies alone, right? There's spectral leakage that comes from just if you have if you truncate the simulation at too short of a time, but that's independent of how many frequency points you select.
Yeah, hopefully that answers your question, Ben. Let's start here with Arjun, and we'll go to Sequoia.
So you're initializing your design region or defining your design region with a much higher resolution than your underlying FTT grid. How do those two play together?
Do you want to just repeat it real quick?
Yeah.
Thank you.
So your design region is defined with a much higher resolution than your underlying FTTD grid. So how do those two resolutions play together?
Yeah, so that's kind of another hyperparameter, right? Like how do you choose a suitable ratio between the two? My rule of thumb is I typically just map to the actual Yeager resolution, which is actually a factor of 2 larger than the normal MEEP simulation. Sometimes we like to go significantly higher resolution such that we can easily, as I said earlier, interpolate onto really fine grids that we need for our GDS layouts at the end of the day. Although, as I'll show tomorrow, that's no longer necessary because we've actually hybridized the two paradigms between density-based optimization, which is inherently discrete at each point, and level set optimization, which is this implicit parameterization scheme. So now you can take something at a normal Meep grid resolution and continuously linearly interpolate your design at that point. Yeah, that's a good question. Sequoia, do you want to get the microphone too? Thanks, Arvin. Yeah.
From your experience designing these kinds of devices and whatnot, is there like some upper limit on dimensions where it gets unwieldy or takes too long in terms of simulation time, like max dimensions? What have you found?
I've easily done, I wouldn't say easily. After about 4 days of computation, I was able to do 25 lambda in each dimension. But I've also lately been able to do about 50 lambda in each dimension on our clusters at Georgia Tech. And you could probably do more depending on how much you're willing to wait. You know, yeah, but 50 lambda in each dimension is pretty large for FTTD. Yeah, Flores, you want to pass the mic behind you, Sequoia? Thanks.
So the backward pass is done in frequency domain. So I suppose you have to do multiple backward passes for multiple wavelength points if you want to do that, or?
Yeah, that's the beauty of this technique is it's just one forward pass and one backward pass. The hard part, as you mentioned, since the backward pass uses those frequency domain values, is now we have to come up with a broadband pulse that corresponds to that desired frequency profile, right? That was kind of the hard PhD problem that we had to solve, which is luckily solved. Yeah, good question.
One more hyperparameter question.
Yeah, please.
How do you decide to increase the discretization parameter, for example? Like,
are you talking about the ratio between the design grid resolution and the?
Yeah, like the binary.
Oh, the binarization.
Yeah, binarization. Yeah.
Yeah. So again, I'll talk more about this tomorrow. But previously, what you would do is you would ramp it up until your gradients started to break down. You'll notice that the gradients actually approach 0 as your binarization approaches infinity, right? Because that discontinuity just kills your gradients, right? But because of this new hybridized technique that we invented, you can actually ramp up beta to infinity. It emulates a perfect level set, which means you get the gradients along the whole boundary, and it works really nice, really seamlessly. I'll show some cool results tomorrow about that.
So it's just automatic, like basically.
Yeah, it's all taken care of under the hood. Yeah, there's still some small things that we're trying to fix, right? But it's pretty seamless. Any other questions? Oh yeah, there's one in the chat, and then we'll go to Dr. Ralph after. Okay, this is from Mahmoud Ruzi. For metals and high Q structure, it seems the convergence is very slow. Tell me about it. Is it possible to improve accuracy by applying appetization before FFT? No, appetization is actually a boxcar appetization. Yeah, so this kind of relates to what we were talking about earlier, right? You could window your response in some way to try to structure or get some sort of structure at the end of the day. I think a better approach would be what I was talking about earlier, where you use a pod A approximation or some other approximate, such that you only have to simulate for a brief span, and then you get the analytic form of the signal at the end of the day, and you don't have to wait for it to queue out. There's some downsides to that because now you have to store your data, not just at every point in space, but at every point in time, so that you can create those fits. So now it looks a lot more like a classic time domain adjoint problem. But I think that's a better way to handle these high Q structures. With regard to metal structures, you know, Stephen's really good at reminding us that there's no panacea for solving Maxwell equations, and FTTD certainly isn't that. So there might be some other tools that are better suited for a lot of these metal structures where you have to resolve the skin depth, and something like FEM, for example, is really good for that. And we're actually going to hear about some alternate techniques during a talk tomorrow as well. So Dr. Ralph, did you have a question as well?
Yes, 2 questions. First, can you explain a little how we don't get too conservative in ensuring that we meet DRC? That it seems that it would be easier to make sure it just meets DRC and then don't try to approach the limit too tightly. That is, how much energy, and is it worth it to spend energy to get close to DRC limit or not?
Yeah, for those who aren't familiar, like we talked about earlier, DRC is the design rule checks or constraints that a foundry imposes on our design, right? And do we need to give ourselves a little bit of padding when we prescribe it? If the foundry says it's 90 nanometers, can I just put 90 nanometers in the code? Or do I need to be a little more conservative and say 100, 110, for example? And in my experience with hundreds of devices that we've actually sent to the fab, I've been able to prescribe the exact value that they provided, and it's actually worked out. And that's actually worked for different fabs, not just one particular fab. So yeah, great question.
The second was, you described how the back propagation computation time was notably longer than the forward.
Yeah, the adjoint run, you mean?
And you were going to say, you said you were going to say some more about why that is. Could you elaborate a little bit more? What's going on there? Why is it really slow?
Yeah, the tricky part, I tried to articulate this. Let me see if I can do a better job, is when you compute the equivalent time domain profiles from your frequency domain quantities, we essentially do a fitting problem. We take a bunch of Gaussians or filter windows that we have to put together. And the width of those Gaussians in the frequency domain depends on how densely packed your frequency points are. So if you need to simulate frequency points that are really close together, we need to resolve those frequency points, which corresponds to really long time domain simulations. So that's the natural trade-off. Again, it's a Fourier uncertainty principle at that point, right? Yeah, good point. Yeah, Ryan?
Yeah, maybe you covered this in a way I didn't understand, but oftentimes when you're interested in optimizing a structure, say for like a fab, you're not interested in just that it will work, but that it will work over lots of different types of errors that might happen in the fabrication. It's like robust to variation. How is that thought about so far?
Yes, the answer is extensively. At least in my own research, that's kind of the name of the game, right? You have to create devices that work across multiple wafers, different operating conditions. Tomorrow I'll give some cool experimental results that demonstrate that it is possible to do that with this platform. The basic idea is you do what's called a robust optimization. You do a minimax or worst case optimization over various perturbations of your design field. So for example, if you expect the foundry to do some level of erosions or dilations, like over etching and under etching, you simultaneously optimize all three of those worst case scenarios. And the optimizer will produce a design that is tolerant to that, meaning it'll still perform well in spite of all those other perturbations. And I'll show some really cool experimental results on that tomorrow. So yeah, great question, man. Any other questions?
So it's maybe a bit related to the previous question, but for DRC, you often have like many different DRC rules, right? You have like feature size, you have distance between things, you have density. What else? You have a lot of different things. Do you all encompass this in your loss function, or do you kind of have yeah? How do you translate all these rules into the loss function if you need to do that?
Yeah, great question. The answer is it's really hard. Yeah. But we did some cool work recently where first of all, we had to invent a bunch of optimization constraints that could account for rules that were previously ignored in a lot of other previous works, but were actually more significant with respect to the fab compared to things like minimum length scale constraints. And the things I'm talking about are like minimum area and minimum enclosed area. So the basic pipeline is to come up with some mathematical formulation that actually detects violations of various DRC rules, whether it's the minimum area or the line width, and then formulate that as an optimization constraint, not necessarily in your objective function, although you could do that, but I'd rather do it in the optimization constraint because the optimizer is forced to satisfy that constraint before it even thinks about the FOM. And to be honest, that's how the fab works too. They don't care how well your device performs. If it doesn't meet DRC, you can't tape it out, right? So the optimizer kind of mimics that philosophy. And now the challenge is just to make sure that you have enough constraint functions that kind of encapsulate that entire DRC rule book, right? And what we've seen actually, luckily, is a lot of these DRC rules kind of spill out into other rules. By satisfying one particular constraint set, it actually satisfies several others as well. So as long as you can sufficiently sample, albeit sparsely, in that space, you could get the entire rule book through an entire optimization pipeline. Does that answer your question?
Okay, new question. Oftentimes, at least when I'm using the topology optimization tool, and I'm not expert yet, oftentimes you like reveal patterns and structures that say, oh, this is kind of what it's trying to do, like across all kinds of design constraints, right? And I have the thought to myself, oh, I'd really like to actually parameterize this as a set of ellipses, this part, and not worry about each individual pixel anymore, or something like this. What might be a good strategy to think about parameterizing to a small number of variables instead of keeping track of every pixel?
Yeah, great question, Ryan. So effectively, you kind of want to collapse the dimensionality of the problem to preserve some sort of physical structure that you know a priori will perform well. You just need to get the exact parameters at that point, right? And to do that, you typically need to do what we described earlier as a level set optimization. And for the longest time, Meep unfortunately didn't support that, but it does now. And it uses the same framework as the density-based variables. So I don't have anything here in this tutorial that describes how to do that, but we do have a few GitHub posts that show how you can do exactly that. You could take a series of ellipses that are parameterized by maybe various radii, for example, and you optimize those parameters, and it'll automatically take care of the material grid for you. And the cool thing is you can set beta equals into infinity. Everything is nice and binary, discontinuous, quote unquote, and it works really well. This is from Simon. Beyond geometry robustness, are there considerations for materials optical constant robustness? How well is it, for example, the polysilicon refractive index characterized on that optimization on the right? Great question. Yeah, so this is where you could kind of augment your robust optimization, where you don't just consider geometric perturbations, but also material perturbations. In your case, you're saying, well, maybe the refractive index is changing because the fab's not perfect. Alternatively, you could say that your device is operating in a highly fluctuating environment where the temperature is changing. That also changes the refractive index. You could still design a device that performs well in spite of those variations, but instead of doing a minimax over erosions and dilations, now you're doing a minimax over varying levels of refractive index, maybe 3.5, 3.4, and 3.6, so that the device at the end of the day still performs well in spite of all of that. I will add too that since these devices are so small, they're kind of naturally not super sensitive to these large fluctuations in refractive index. It's not like you have this really long directional coupler, right? But that being said, you can still explicitly make your design rather robust to these perturbations. And then another question from Ben, probably for Stephen. He says, Stephen, could you post the GitHub post that talks about level set optimization? I'll post it after. I don't know if Stephen knows which one I'm talking about. It's in the discussions.
I'll wait till you find it.
Yeah, I'll take care of it. Yeah.